So now I have the pleasure to introduce the wonderful Devis Tuia to you. So he'll give us the European perspective on the topic of biodiversity modeling. He did his PhD at the University of Lausanne. And after many stations across Europe and the US, he then returned to Lausanne, to EPFL, where he now leads the team, excuse me for a second, dubbed Environmental Computational Science and Earth Observation Laboratory in the small town of Sion. And he does a lot of biodiversity modeling, as we have already gotten a slight introduction to, along with a lot of different environmental topics, using all kinds of sensors that you can find, with a special focus actually on remote sensing. So now let's give it up for Devis.
Okay, good morning. How are you? Come on. I mean, you traveled a long way to be here. Let's be happy to be here, no? Okay, so Sarah has already told you about our overlap in topic. That was completely unplanned. But yeah, I mean, you get 2 SDM talks for the price of 1. How cool is that? And yeah, I'll do my best to give you a different perspective, but you know, some elements will be redundant, and at least I don't have to explain SDMs again. Thanks. Good. So the idea of this talk is basically to basically have a walk in our experiences with deep species distribution models from the very beginning of our adventures at ECO, at EPFL. It is the work of a bunch of people in the lab who has been working very hard on all this. Why am I excited about it? It's mostly because, well, we are living difficult times in terms of biodiversity crisis. I guess most people here in the room are aware and concerned about it. We need to find ways actually to is there a pointer here that I can use? No. Okay, I'll do without. Yeah. Well, we need to change the inflation of this curve, of course, and try to get something more sustainable, hopefully the green one, where we can preserve biodiversity and all the services nature gives to us. Because it gives us a lot of those services. So, I mean, if we have medicines, if we have food, it's most for a lot of, also thanks to the different species that thrive in our planet, and we need to protect all this. Okay, this is a kind of a humoristic quotes about the crisis hitting us. Then it's up to you to decide whether it's the biggest one. But you know, they are all related and they're all hitting together, which is not something that we want, of course. Okay, so my little contribution to this pile of problems that we want to tackle and hopefully solve as a community is, you know, mapping of species, of all the distribution, and I think this is necessary for effective conservation targets. So that's why a few years back we started working about species distributions, and that's also why I think it's very cool and important to be on this wagon. So if you want to join the wagon, if you haven't yet, you know where to find us. Okay, so the talk is going to be in 3 parts. For every part, I have a little bit of fun with DALL-E to create an image that characterizes it a little bit. So let's start with our very first steps in SDMs. So you will see that there is no deep before SDM here. So that was where we're doing cool traditional stuff. And that's basically based on the paper by Nina that you will hear about in a second. Okay, so question for you, because you look a little bit sleepy. So how many species of trees are there on Earth? 20,000. Who says more? 100,000. Who says less? 10,000 is not between 20 and 100. Damn! Okay, 73,000, more or less. And I mean, that's what Nina told me. I believe her. And yeah, you know where they are? On Earth, yeah, thank you. So, someone said so. In the tropics, a lot of them are in the tropics. Good answer. Well, but the true answer is that, you know, we don't really know. We know they are in the tropics. We know there are not much in deserts, but exactly, we would like to know a little bit more, also because there is a bunch of people around, very, very busy taking measurements. We've been talking about iNaturalist. There are countless incredible ecologists taking samples, and we can leverage all this to understand more where they are. And the last question that we wanted to tackle is where will they be? Because, of course, it's good to know where they are today, but it's also maybe be good to know how these distributions will change in time, because future is what we are betting on. So we want to, create policy that will help us having better, healthier, and better distributed tree. But this is obviously climate dependent, and so we must have an interface with climatic models that will help us making this kind of projections. Okay, so now that we have set the stage, the slide that is completely useless is to just tell you what a species distribution model is. But I have nicer satellite pictures than Sarah, so please pay attention. So the thing that we're trying to do is basically to get to this type of maps that will tell you where a species is. And to do so, we start by these environmental covariates, which is a bunch of data about soils, about temperature, precipitation, you name it. And we try to connect these environmental covariates with observations that can be presence-only observations, so people walking around seeing a species and they tell you, is it there? But they don't tell you where it is not, and that what I called presence-absence, which is detection and detection, apparently, from today on. And I will try to use this terminology. And we have a model here in the middle that tries to make these maps, and then we will see ways to try to project that in the future. So briefly, Nina went through a lot of putting together different data sets of observational data, and we could provide, calculate, map roughly 10,000 species of trees all over the world, and with an accuracy that was, decent, so around maybe 50% on the validation data. Remember, we're talking global distributions at 1 kilometer resolution, and this was basically a set of maps that we disclosed, so you can get there, you can play with them if you want, and use them in your research. Everything is open, and it's kind of nice because now we know where they are, in a way. It's 10,000, it's not 73,000, I get it, but that's the best we can do with those data that we had. Now, if you have 10,000 single maps, you can, of course, overlap them and then make some kind of count of different species. And, of course, Usei in the tropics before was obviously right, like many of the species live there, which also help us studying the range, the competition, this type of things. And this is something that we can do because now we have this precise map for 10,000 species. But of course, we didn't want to stop at the today's situation. So we run a number of climate model, basically, to see what our inputs, that will be this temperature, precipitation, and all this kind of prediction, will look like at the 2100 horizon. So basically projected the inputs of the model in the future, and then run our models again, and compare the different maps. And then this could, help us reflecting a little bit of how these distributions will change. In this case, we tried not to disclose the exact map because then people will say, oh, but in this specific 1 kilometer pixel, this is absurd, which, fair enough. I mean, these are models, these are projections. So they are naturally imprecise. But we can see trends. And we can see trends, we can see, for example, the latitude shift of the forest to see who is winning, who is which biomes will gain species. Boreal forests will probably because there is more space, and we can have all this type of reflection of what will be going on with the world's forest in 80 years' time, which is basically day after tomorrow in our scale. And finally, since the maps are now openly available, we're also starting to work with our plant ecologist colleagues, which are mostly interested in things like thermal safety margins. So to see in which regions trees are undergoing excessive thermal stress, meaning that we are crossing our distribution maps with temperature maps and see in which regions of the tropics we are going beyond what we call a critical temperature, which is a temperature beyond which leaves of a plant starts to die, basically. And everything that is red in this map are regions where this threshold is exceeded at least 1 month in the year. So these are areas where we are seriously in trouble. Fortunately, there is a lot of green areas in here, so that's good. But at the same time, this is the type of research you can enable if you have this type of species distribution maps. Sorry for the terrible quality of the graphics. That's on me, not on the students. That's on me, screen capturers. Okay, right. So all this was some kind of traditional SDMs brought at scale thanks to large-scale remote sensing products. Can we now move into deep learning and SDMs in our research? And so we were 2022 to 2024, so we're still figuring it out whether it makes sense actually to move into the deep learning. So Sarah has gone some serious argument that it makes sense. So this was our first adventure in the realm of DeepSDMs. And we start from here. So this is still nothing to do with deep learning. So this is a paper by Valavi et al. In 2021. And they compared a bunch of methods. So every method here, every little square here, it's one of these methods applied to one species in a different region of the world. Okay? And if you look at the graphic, I mean, there aren't so many big differences if you look vertically. It seems that most models are doing similar performances, right? So that's okay. It's very tough to beat, for example, a traditional method like Maxent. And even if when you start using neural networks, like the multilayer perceptrons, we always are more or less in the same ballpark. So why at all going into deep learning? But first of all, we make the bet that the relationship environment-species are nonlinear, and that we can catch them with this type of models. We also want to have multi-species models, which is something that methods like Maxent cannot give you. So that's our single-species model. So we have 50,000 species, you train 50,000 models. And so with an MLP, with a deep learning, it's a debate whether a MLP is not a deep learning model. Let's not enter that. So we can predict multiple species at the same time, which is something very, very valuable because you speed up things significantly. And then not only you can predict more species, but you can easily, let's say almost by design, you have ways to integrate different types of data. Sarah showed it for the camera traps environment and satellites. We can think of like time series. We can think of text, like in this very interesting work by Hamilton. And the sky's the limit when you have a model that is flexible enough and you can take data, encode them in some way, get a vector, and start to put it with your traditional data that you know very well about temperature and precipitation. So that's where we started to think about those things, and this was like a very first SDM approach by Benjamin, who is in the room. Where are you, Benny? You're there. Hey, how are you doing? And then, yeah, we worked just with raster data. So it was the satellite images, some altitude, land cover maps, and we tried to combine them by stacking the vectors and then having our MLP. And this gave us hope because the things were working okay. After that, we tackled the problem of presence only that has been discussed in the previous talk. And in this case, we were trying to trick the model into not only using the species that was observed at that place, but also we will say, okay, if it's in a radius of reasonably close and we have seen another species, then we can swap the labels. Because if I see a certain flower here, it's probably there as well. Unless there is a very strong barrier or something. So we were tricking the model by data augmenting our labels in a very spatial way, where we will just swap the different labels. And this kind of worked. So this was the GeoClef 2022 entry, and you know, we got second. And even though Benny tried to conceal his identity by a Japanese-sounding name for the team, that was us. And this was just by using this label swapping story, and you know, it made the trick, especially on the test set, because we were a little bit more robust. And okay, so we had some deep learning models that were kind of working. We were state-of-the-art across all this community of you know, deep learning enthusiasts trying to make their way in ecology. And then we started to look a little bit also on the predictor side. And here we were a little bit looking into the literature where most early approaches were basically taking all their inputs, stacking them into a big cube and pushing them into the latest neural network. And we kind of realized that these predictors, they had very different scales. No? So having a certain convolution filter, if you allow me, on a predictor like a satellite image where you have a metric resolution or some climate data that is at a kilometer scale, do not mean the same at all. So we were a bit surprised that early approaches were just considering that everything was the same. And we tried to have a look into that as well. And this is a work that we recently completed. And we were basically comparing a bunch of approaches that were multi-scale and multimodal. So this will be like a traditional approach when you have some climate data, you push it through a neural network, you get some features, and then within this feature, you learn some local descriptor that you push into a model. So single scale, single sensor. Oh, sorry, yeah, you extract image features, focus on spatial scale, and classify. Sorry, that's us. Yeah. And then we started to look at, okay, what if we do the same, but instead of focusing on a single scale, we get multiple ones, and then we get multiple features, and then we combine them in the classifier, which is also pretty standard, I give you that. But then we have independent vectors at different scales that we can analyze, right? So we start to having a little bit of insight of which scales are important and these type of things, and we know that this is very important for a biologist, even though it maybe doesn't change anything in terms of performance at the end. And third, then we started to look between sensors and doing a similar job, like now that we combine environmental data and satellite, very similarly to what Sarah presented before. Maybe you could add a camera trap here. Our features are less fancy, no Dino V3 here. But the idea is very similar, extract something useful, and from there, combine and classify. And yeah, the results were very, very interesting. The paper is now under review, and fortunately, the multi-modal, multi-sensor model is out there. So combining the different sources of data makes sense. They bring you different information, as you said before, Sarah. We also looked at into different for amphibia, coleoptera, and the trend is the same for all of them, which is very reassuring. This is for some Swiss data from InfoSpecies and InfoFauna, if you want to know. And yeah, so it kind of makes sense to look at different sensors and also across scales. So you see here the benefit of combining multiple scales. It's like always on the positive side. So every time you combine scale, you bring in something useful. So okay, why not to do it? How am I doing time-wise? Oh, I'm doing good. Yeah, I'm going very fast. Yeah. Sorry, I had my coffees and then I get very excited. How are you doing? Good, nice. Okay, so this is like the way we were looking into those things in a pretty explorative way. We wanted to understand what we were doing, even though we knew that also just going with a single model will make the job, but we try to understand the different components and the different inputs. And I think it's valid points and really give us, in a way, a legitimacy to keep going in that way and to think that we are relevant in this space. Now, I wanted to show you like our last adventures in the realm of SDM. That's the work of Robin here in the first seat. And we have been trying also to look a little bit more into the multimodal side of things. So it's a kind of a spiritual step forward of the work I presented before. And basically, we also started thinking that for different species, we don't forcibly need the same predictors. In different places, we maybe don't have the same input data. And these are limitations that will basically force you to train different models everywhere. Why don't we think of a way of learning models that can accommodate a bunch of different inputs and be robust to the situation where you have or you don't have a predictor of the other? Okay? So again, we will be working with a bunch of modalities: satellite data, time series, some climate, environmental raster, location, you name it. So no camera traps, sorry. Yeah, we try to make sense of all this in a single modeling framework. Okay, now you're all experts of species distribution models. So some of you are ecologists. So what are the things that you would like to have given this context? Feel free to shout. Sorry, what? Accuracy is good, you will have it. But that's not on my slide, so I will not. It's implicit. Interpretability. Yeah, I will put it on later because it's not the first. I did that at another conference and it just came like in the right order. I was so proud of myself, but that's not working out as intended here. One last chance. Generalizability. Okay, this works. So sometimes you have some predictors, sometimes you don't. So you want to be general to the absence of predictors. Rock and roll. Very good. Next. Correctness. This is a bit of curious, yeah. And I don't have it on my slide. Come on, just find the second one. Sorry? Yes, you will have it. It's the third. I need the second one. Help me out. What does everybody want when you give a model that works? What does the person who's paying you asking you? Oh, you have good accuracy, but uncertainty and flexibility. Flexibility, yes. So it's the possibility of, taking the right feature for the right species and being able to tell me which feature is the important one, which leads us to explainability that was raised by many, many people. So, okay, I'll probably turn things around for next time I give this talk. Yeah, I mean, it's very easy on PowerPoint. It's okay. And we try to do all of this with MaskSDM. Okay, that's our bet, is that this model can do all of them. So basically, when you have a traditional species distribution model, what do you do when you have missing values? So if you have a full modality that is missing, you just forget it exists. Okay, so I don't have it, it doesn't exist, and I will do my model without. If you have the modality, but sometimes records are missing, you will do what we call imputation. So you will do, I don't know, an average of the value before and after, or replace it with a number it means you don't have data, or things like that. Okay? You will do some kind of imputation. Here, I guess the name of the model gave it away. We will look at masked modeling, which is something that is being introduced in models like BERT, in natural language modeling, where basically the task is to predict the next word. And when you train, sometimes you will mask a word and try to predict it. Okay? What do you do by doing that? Is you train the model, then when something is missing, you can still do the job. Okay? And we'll do that in species distribution models. Okay, so by design, this is exactly what we're doing. So at training time, you will have all your predictors as inputs, right? Sometimes they will be missing. So we will replace their feature after tokenization by a masked feature that basically is learnable, and it says, I don't have this data, please don't use me. And sometimes during training, we will have the data, but we will mask it anyway with a certain probability p. Okay? So by doing that, we will train the model to be able to predict even when it doesn't have some of the inputs. So that at inference time, so when you predict on new data, well, you don't need to mask by probability P anymore, but the data you don't have, you will just use your masked token, and the data you have, you will pull them through, have your feature, put them in the transformer, and predict your distributions. Okay? It's like masked autoencoders, if you are familiar with this type of things. Okay, good. So we work on splot open dataset. So it's a data set about plants. It works by plots. So we have 90,000 of them, and we try to model 10,000 species, and we just kept those for which we have 20 observations. Less than that, it's a little bit not enough. It's presence absence or detection non-detection, and it's open, so you can also get it yourself for your own research if you want. And it's not our data. It's been done by some very clever people. In terms of inputs, so we have a bunch of them. The table is way too small to read, especially for you guys, cool kids in the bus back there. But just follow the little thingies. So we have some climate data, some soil ones from soil grids, topography, location, longitude, latitude. Something on human influence is taken from OpenStreetMap, bunch of things, and then the metadata. And some SatClip embeddings. SatClip is some satellite embeddings. They're from Mark. Where are you, Mark? There you are. Cool. And so they basically, you take a satellite image, encode it, and it gives you a vector. And we use that because it's much smaller than downloading the images themselves. So we have all these different modalities and put them into the mask SDM. OK, so remember, it's a single model. Okay, it's one model we train with all this on splot. When we have the data, we use it. When we don't have the data, we mask it, and so on and so forth. So with a single model, when at inference time you do with what you have this type of performance. So the thing that I want you to see is that the performance is stable. Okay? Except when you use only temperature to predict the distribution of 10,000 species. Fair enough. But when you have other variables, and at least two of them, you're going more or less on the 90+ type of accuracy. And the good thing is that this is very similar of when you train and test with that specific amount of predictors, which is what we want to achieve. No? We want to be as accurate as if we train specifically for that with a model that is trained on everything when you have it or you don't. Okay, and I think this is very powerful because basically it leaves you the opportunity to use what you have at the location that you are observing, and then leverage all the benefits of all the other data you have been training on. It's very fast at inference, right? Because you just take the data you have, you mask the rest, and you predict. Which also means that you can have fun masking the different inputs and then get the performance you will have if you had only one or another, or if you have everything but one or another. In this case, so we try to make like this combinatorial analysis of seeing which types of features were the most important. So here we get to the explainability angle, where we can see, the environmental variables are important. Then, if you want to then know how this 92% splits into sub-features, you can also do it. You just run some more forward passes by removing one or the other, by masking one of the other, and then you get your total. And this becomes a very flexible and efficient way of doing to do feature importance in a data set, especially when you have a lot of features. And then, of course, you can map them. So you can predict all of your grid just with a subset of the data, and then you can see the distribution of your one species when you use only a subset of your parameters. And it's funny because these also show you the numbers are a bit deceptive, right? So if you look at the map only with temperature up there, sorry, I'm a short man, so I cannot get up there. But the temperature one there, it's 88%, and the one with all the predictors is 91. What's 3.5%, right? Well, look at the map. It's a lot. So that 3.5% is really a lot, and this allows you to visualize all that. So I think it's a good way also to make this type of reflection and see what predictors works, what not. And you can, of course, modify that per species. It takes seconds to get one of these maps. Woo! Okay, we are there. I hope it was interesting and a fun ride in the beautiful world of species distribution models. If I have a take-home message to give you after 3 years of DeepSDM and maybe a little bit less of 10 years in SDMs in general, well, it's technology that can help you to map a lot of species and to do it at large scale. And I think this is powerful in the way that you can have these global maps. If you select your predictors right, you can project in the future. It gives you a lot of evidence of this type of distribution. It's something that was difficult to do before in a precise way. I mean, we're talking about global maps at 1 kilometer resolution. So it's something that I think can be very useful for policy, for decision maker. I mean, maybe I'm wrong, but that's my hope. There is also a lot that is still to be done. So, we've been working with tabular data a lot, a little bit with image data. There is so much out there that we are not considering at all. We're not considering text, so mirroring what Sarah said before. We're not using, food webs, predation, all the things that, ecologists know very well. And I think there is a lot to be done in synergy between these communities that, way too often just look at each other from far away and maybe don't understand each other very well, but we're working on that. We'll keep working on that. If you want to be part of the adventure at the World Biodiversity Forum in Davos, we will have a session about DeepSDMs. It's even being extended beyond DeepSDMs at the moment. So send an abstract, come and discuss with us. It's going to be a big pleasure. And before concluding, I just wanted to give a shout out to the people who really did these jobs. I mean, I'm just a messenger. They did the job. And so these are my wonderful colleagues at EPFL or at different institutions. They do a great job, so they need all the credit for everything I presented today. Thank you very much. That's part of the rest of the lab in our excursion last week in Lauterbrunnen. It was very nice. And I mean, if you want to chat, I'm here all day. It will be a pleasure. If you have any questions, here I am. Thanks.
Okay. Thank you very much for the amazing talk. We now open the floor to questions, and I think already Konrad here.
Thanks, Devis. I like the masking idea because this problem with predictors being very unevenly distributed and sometimes not there is very prevalent in this space in practice.
Yeah.
One thing that that jumped to the eye, and I would like your opinion on it. You had in your comparison table 90+ number for location only and an 80 for temperature only, which you can see as a rough proxy of latitude. Mm-hmm. So how much of a problem is memorization in this SDM modeling with very powerful models? Because I have been plagued by it, and I feel like if you can do 90% from the coordinate alone, are you actually learning by heart the lookup table of the Earth?
I don't know. I mean, if you look at the maps, if I go back, it seems that even the 88 to 91% is very different spatial patterns. So I guess the memorization gets you so far. Probably the AUC is also not the strongest metric to look at these differences. But I think that 3% difference says a lot in terms of distribution. And it's something maybe you don't catch with the global metrics because they are very sparsely located validation points. But I mean, that's a guesstimate at best.
Yeah, I think evaluation is like the most interesting scientific problem in this space, right? Like, how do you convince yourself that the model is actually working? And so I guess along those lines, like what you didn't talk about is like what the choices you made were for evaluating these models in terms of things like that spatial autocorrelation that can happen or like this memorization. So like, how did you choose what to hold out and what to fit
So we always use a, do I see it in the map? I mean, it's very small, but the data set is distributed the way it is. But we used a block separation. So everything that is in green here is training, blue is validation, red is in test. And we basically make a checkboard pattern over the Earth, and we try to take this a little bit like you did, maybe not as with as big checkboard patterns, but I mean, locations that are close are generally in the same set. Let's put it like that. Yeah. We could do like continent-wise validation. That would probably be more harder on our metrics, for sure, but also something that will push the generalization argument even further. Like to say, if we train in Europe, can we predict in South America? Sorry? How many species overlap? That's another question. Yeah. Functionally, I mean, I guess there is a million ways we could do it, and that's definitely something we should discuss as a team. Yeah. Thanks.
Thank you very much. I wanted to ask you if you have already tried, or if you have concrete plans in mind to pre-train the transformer using maybe something like an autoencoder, and
well, where is the diagram? I mean, at the end of the day, we need only the encoder here because we are doing species distribution. So at the end, we're trying to predict the probability of belonging. Like, why will we need just for pre-training? You mean?
Yeah, I was thinking that obviously we're using correlations between the different modalities, and if you were to do kind of an autoencoder pre-training, then we might, as in language, have a better generalization in the end.
I mean, why not? You could take the inputs, encode them, decode them, pre-train like that, and then tune it like that. I mean, it's a strategy. It could be, yeah. We're doing something like that for like multimodal satellite data. That's a model called SMARTIS that we have at ICCV this year. It's another strategy, yeah.
Thank you.
Thanks.
Yeah, thank you very much for this presentation.
Sorry.
Your right, all the way.
Yeah, you are. Sorry.
I really appreciate your energy and the engagement in the crowd and just kind of sharing facts. Reminded that I failed physics in university. So my question has to do specifically around reforestation with natural species and the introduction, particularly throughout the Global South. I'm thinking of like Niger and Tanzania. With such models, are you able to look at specific species over a period of time? Because the guesstimate or the estimation hypothesis around reforestation with natural species would be, or indigenous species would be faster. Thank you.
Okay, I think an answer could be that we have here technology that can be used to map those species. I don't know if they are among the species we are using right now. So the 10,000 species we have right now were based on a lot of data set from the field of observations of those. If it's not, and you have such data, we can give it a try. The base technology remains the same, just the model needs to be updated with the extra species. And then when you have that, you can use that as a support for the reforestation policy you're designing. It will not solve the problem of reforestation by itself, let's be clear. But I think it's good evidence that then you can use to see the success of what you have been doing, especially because climate data you can get in the past, satellite data you can get in the past up to a few years. So you have all the ingredients to have this type of analysis. Yeah, that would be nice to do.
Hello, thank you very much. I'm here.
Can you just?
Yeah.
I don't see you. I'm there. I'm not doing that on purpose. I'm just blind.
No, thank you very much for the talk. It was great and inspiring. I come from ecology, and there we do a lot of measurements on species and shifts. And what I observe is that sometimes climatic drivers predict a rather optimistic shift, I would say, whereas our field measurements are showing rather a slower shift. So how have you noticed, you have human footprint there, and there are multiple human variables, I would say, that limit species distribution, beside climate that shows the potential distribution, but humans rather can slow that down. How is the human footprint reflected in your models, and how is that, what's the importance of that variable?
So, good points. So in the first analysis, the one on the global distributions of trees, since we wanted to predict in the future, and we needed to work globally, we limited ourselves to climatic drivers. So, I mean, I will not go back to all the slides, but we were inputting temperature, precipitation, soils, so variables that we had globally. The problem with human footprint is that it's very good in northern countries, and then it degrades very quickly in southern countries. So it's something we didn't want to use in that analysis. So I don't really have an answer for you for that. Here, we are using some of it. Here, I will move. So there are some such variables in our set. So, and I mean, now I'm just guesstimating. Yeah, we can see here with the variable analysis that by itself it doesn't explain much, but it still helps you with all the others to increase even more. So it's one factor that for this specific analysis seemed to have played a role, but not a major one. And that's as far as I can go with the analysis I have at the moment. Yeah. Thank you.
Hello.
I saw you. It's okay. Have you?
First of all, thank you for the talk. I have one more question regarding the accuracy of the model. So what are the missing 8%? Where does the model actually fail? What are these outliers that are hard to predict?
I mean, our labels are not perfect either. So I guess a good part of it is imperfections in the label and things that we just don't see. There are species for which we need to be close with a camera trap, or things happen beyond resolution. Imagine there are some, I don't know, I mean, sorry for biologists, please do that. There must be a very tiny little frog that lives in a very little pond that is completely invisible in all of this data, and we'll never be able to catch that. So I think that those 8% are somewhere in there. Yeah.
So do you feel that's certain data you're missing for the model? You just need a better model? Like, what do you need to get closer to estimate these 8%?
All of the above, no? Better data, better result, labels that I'm sure are correct, all of this in unison. And then there will always be something. I mean, if someone tells you that their machine learning model is 100% accurate, they're lying. They're just lying. There's no such thing. There will always be errors. Yeah.
Thank you.
Sorry? What we have here is as good as we get it. What do you mean? Yeah. I think so, no? Because if I look at the maps that we are getting with the full model, we're getting close enough. Yeah. So from an accuracy perspective, you want to get to 100%. Then, yeah, that means Sarah's touching another point, is that maybe on the deciding end, 92% is enough, because this map is good enough. So we always want more. You know, I have some projects in the humanitarian sector, and I always come with the accuracy arguments, and they're like, man, I know that there is something going on here. That's enough. I don't care if the outline is exact. So yeah, I mean, it's also a question of what is needed. Yeah.
Hi, I'm just behind the guy who asked your previous question.
Oh, you're very nice, helping me find it.
It continues with the accuracy question, actually. And I thank you for sharing your secret of so much energy, bringing energy in the room. So I was thinking more from ecologist perspective that this problem must be the species distribution must be long tail. Like the distribution of species would be long tail.
It is.
And let's say this prediction map of this species that you're showing. So how does your evaluation metric take the rare species into account? Like, so, because I don't know if this species is the most common species in the data set. Or
it's a fair point, but it's also a question I cannot answer right now because I don't have it here with me. It is long-tailed, so the moment you get to species for which you have 2-3 test samples, it's going to be flipping a coin. And also because those same species are not well represented in your training data. And I think that's where the inclusion of subsidiary information helps. Like if you start considering, species interactions, food webs, that's where you can lift up for those species for which you don't have observations. I think it's already better than single species modeling. If you have 2 samples and you run a maxent on this, oh, I'm sorry, with 2 points, what can you do? So by having this multi-species prediction, I hope that those with more data help those with less data, and that's something we observed in the other studies about the scales, but we can only get so far. I think that introducing all this other information about predation, interaction will help, because if you know that the predator is around, probably the other species is around as well.
Wonderful. Thank you very much. Here's a small...
Thanks, everybody.
something.
Oh, thanks.